So we've got another interesting problem for us to do today. A speeding car passes a parked police car at a constant 34.0 meters per second. The police car starts from rest and accelerates at a constant rate of 2.59 meters per second squared. So it's a three-part question. How much time does it take the police car to overtake the speeder? Part B, how far does the speeder go before he's overtaken? And part C, how fast is the police car traveling when he overtakes the speeder? So let's think about this problem. We've got two things going on here at the same time. We've got a speeder and we've got a parked police car that then accelerates and catches up to the speeder. Both of these things are happening at the same time. So let's just kind of illustrate that with these two markers. So the red marker, that'll be my police car, and the black marker is going to be the speeder. So here we go. The police car is parked there. Along comes the speeder, 34 meters per second, 34 meters per second, 34 meters per second, 34 meters per second. As soon as they're side by side, that's where the problem actually begins. So it's always important to understand where a problem begins and where it actually ends. Because if you don't, you're going to start bringing additional forces and additional information into the problem that is just going to drive you in the wrong directions. So keep that in mind. So the problem begins when the two cars are side by side. And then this guy, obviously is continuing to move forward. The police car takes off from rest, begins to catch up. And then finally, when they're side by side again, that is when the problem ends. So keep that in mind. Now we're going to go ahead and draw two different diagrams side by side that capture that information. So here we go. I'm going to go ahead and draw right here. So there's my speeder, and he's going in that direction. And I'm going to go ahead and label that speeder, and that's good to do. Now let's go ahead and label the other diagram. That's going to be the police car. There we go. Just to keep our information straight. Now the speeder, when the problem starts, the speeder is going 34.0 meters per second. And the speeder continues on at that constant velocity for the rest of the problem. That means when the police car and the speeder side by side, speeder's still going 34.0 meters per second. The velocity has not changed. So what does that tell us about the acceleration? The acceleration, in this case, is going to be 0, right? If our velocity is not changing, then we have no acceleration. All right, what else do we know? Initial velocity of the police car was 0. We don't know the final velocity of the police car. It's definitely not 34. In fact, it's going to be more than 34 because the police car has to catch up and overtake the speeder. And there's only one way to do that. Go faster. All right, so I don't know that final velocity. In fact, that was part C. We're actually looking for that. We do know, let's see. Oh, we do know the acceleration here for the police car. So the police car accelerates at 2.59 meters per second squared. So we do know that. And we're trying to find the time. And it turns out the time, because the problem starts when they're side by side, and the problem ends when they're side by side. So the time's going to be the same. The time is going to be the same for both. So both of these events have time in common. What else do they have in common? Just take a look at that diagram. Notice, same length, same length. Their displacements are also in common. In fact, we actually have to figure that out in part B. Part A is time. All right, so that's pretty much it. That's our information. Two diagrams, two separate things happening at the same time. They've got time in common, and they've got displacement in common. I don't know what these numbers are, but I know the time for this is going to be the time for that, and I know the displacement for this is going to be the displacement for that. So part A, I need to find the time. So I definitely need an equation that has time in it. But this is the part. This is the mathematical part here. I gotta somehow relate these two equations to each other. And they're related by time, but I also need something else that relates them too, which will become clear in just a second. And that something else is going to be displacement. So what I'm going to do is this. This is going to be part A, and I'm going to say the displacement of the speeder is equal to the displacement of the police car. These two displacements are going to be the same. Then what I'm going to do is I need to pick an equation for the speeder and for the police car that have both displacement in them and time, which I'm trying to find. They need displacement because I'm setting these two equal to each other, and they need time because, hey, I'm trying to find the time. So I'm thinking of this equation for the speeder. Average velocity equals displacement over time. I got the displacement, I got the time I'm looking for, and look at that, I know my average velocity. It doesn't change. So I'm actually going to use that equation, and I want to get it in terms of x. So I'm going to go ahead and simplify and move things around a little bit, and I'm going to end up with displacement equals average velocity times the time. I'm going to go ahead and I'm going to take this v times t and substitute it in. Average velocity times the time. Now, let's do the same thing with the police car. But I don't know the average velocity of the police car. I don't know that. So I'm going to choose a different equation for that. And I'm thinking of this equation right here. Displacement equals the initial velocity times the time plus 1/2 at squared. It's got the displacement, it's got the time. In fact, it actually has the time twice. Same number, just happens to appear twice. Now the nice thing about this is this. I'm going to go ahead and simplify this. The initial velocity of the police car is 0. 0 times any time is what? 0. So I can actually eliminate this term right there. And then 1/2 at squared. That's what I'm left with. So I'm going to go ahead and I'm going to take this and I'm going to substitute it in for the x of the police car. So 1/2 at squared. Now I'm looking a whole lot better. I can simplify this even further because these two times, whatever the number is, I don't know what the number is yet, but whatever it is, it's the same number. So I'm going to go ahead and divide the left and divide the right by a time, by a t. And then that's going to give me average velocity equals 1/2 at. Now I simply substitute in. Now be careful here. This information pertains to the speeder, so I got to use the speeder information for this on the left. This equation here represents the police car, so I can only stick in police car information. Be careful about that. You can't mix and match. So average velocity for the speeder, 34.0 meters per second. 1/2 the acceleration for the police car, right? Because this is all police car information, 2.59 meters per second squared. And then I'm looking for the time. So again, I want to divide, I want to get time all by itself. So I want to divide both sides by that. And when I do that, my time comes out to be 26.254. 26.254 seconds. Oh, let's see, I got three significant digits, so 26.3 seconds. That's going to be my final answer for part A. So it takes the police car 26.3 seconds to catch up and get side by side to begin to overtake that speeder. All right, let's take a look at part B. I'm going to do part B right here. So part B, I actually want to find the displacement. The displacement. So this is what I'm thinking. I've got an additional new piece of information, and whenever I use that new information, I want to use the unrounded off number. So I'm looking up here, I'm looking at this equation, I'm looking at that equation. I'm even thinking, you know, could I use a different equation? That's possible too. But this is probably the simplest way right here. I'm going to go up to this equation. I've got the time, I just found it. I know the average velocity of the speeder. It's this right here. So I know the time for the speeder. That's the same time as the police car, but I know that, I know the time. I know the average velocity of the speeder. Hey, I can find the displacement of the speeder, which is also the displacement of the police car. I can do that. So let's go ahead. So average velocity equals displacement over time. The average velocity is 34.0 meters per second. I'm looking for that displacement. And then the time, hey, I just found it here. So I'm going to use the unrounded off number, 26.254 seconds. I want to get this guy all by itself, so I multiply both sides by this. And my displacement turns out to be 892.664. 892.664 meters. I'll round off to 3 significant digits. 893 meters. And we're done with that part. The final part of the problem, part C, is I want to find the final velocity of the police car. Now, because I'm trying to find the final velocity of the police car, I got to use what? Police car information. Time is also part of the police car information because they're both the same. Also, the displacements are both the same. So I've got all that information. I've got the initial velocity, I've got the acceleration, I've got the time, I've got the displacement, and all I got to do is find the final velocity. All right, so the equation I'm thinking of here is going to be this. Final velocity squared equals initial velocity squared plus 2ax. I'm looking for the final velocity, and I need to know all the other information. Do I know the initial velocity? 0, I do. Do I know the acceleration of the police car? I do, 2.59. Do I know the displacement of the police car? Yeah, it's right here. In fact, that's the displacement for both vehicles. So now I just substitute in and solve. I'm looking for that. The initial is going to be 0 plus 2. The acceleration, 2.59 meters per second squared. And the displacement, I'm going to use the unrounded off number, 892.664 meters. And I want to make sure that I use the unrounded off number because I'm going to round off at the very end. And I don't want to use a rounded off number and then round off again. That's going to get me further and further away from the actual answer. And then whatever that is, take the square root of it, and I end up with 68.0 when I round off meters per second. And that is how fast the police car is going when they're once again side by side. So, interesting problem, and that's it for this problem.